Hi, I'm an old guy and I do maths. Today we're going to have a look at how you navigate your way through the many forms of quadratics that there are. Now, this video was inspired by a student of mine who wanted to revise quadratics, and what became obvious when he approached them was that he didn't really recognize the different types of quadratics that he was confronting, and therefore he really spent a lot of time trying to factorize quadratics, unsuccessfully sometimes, because he was going about it the wrong way, because he didn't recognize the type of quadratic that he was looking at. So what I've done is I've divided quadratics up into about 4 or 5 very, very crude categories. Really, for the most part, based upon the number of terms that is in each of the quadratics. So we've got 3 here, each one with a single term. We've got 3 here, each one with 2 terms, and so forth and so on. An exception is when we get to turning point form, and just down the bottom of this page there's this quadratic which, well, I'll get to that. There are a few ways of approaching this. Okay, so let's start at the top. Now, this, and this are all quadratics whose graph passes through the origin. So if I were to draw one of these, well, maybe 2 of them, I'll draw this one and this one, because this is merely a dilation factor, the 3 here. Okay, so the first one, y equals x squared, looks like this. This is very, very rough, but it's centered on the origin, and so the solutions for this, if you are looking for solutions for it, would be that x equals 0. And that just tells you the point where it hits the x-axis and, coincidentally, the y-axis. So because there's nothing else to this equation, this is what it looks like. The other one, which was y equals negative a half x squared, is simply upside down, centered on the origin, the y-axis, and passes through the point 0, 0. This means that it's inverted, it's upside down, and this is a dilation factor. You'll see that it's slightly wider than that. Okay, so that's those. So when you see things that look like this, and they have only one term in them, they're centered around the x-axis and the y-axis intercept, and so they hit in one spot, and that point is 0. Now, moving on, we have a number of quadratics with 2 expressions in them. Now you can see that each one of these is slightly different. What we're going to do is we're going to start over here with this one, because hopefully that's recognizable as the difference of 2 squares, dots, or the difference of perfect squares, dots. And the minute that you see something like that, y equals x squared minus 25, hopefully it rings this bell. Okay, so it's about recognition. And it's important that it be in this form. I mean, it could be negative 25 plus x, or it could be something plus x squared. It could be written in some other order, but essentially it looks like this. It factorizes like that. It is the difference of 2 squares. This and this are not. This one has a plus sign in it. This one, the one we've just done, has a minus sign in it. This one, so y equals x squared plus 25. So just bring that down so that you can see that. When you graph it, what you get is you get something that looks like this. And this point here, wildly out of scale, is 25 on the y-axis. So one of the things that you can say is that you don't factorize this as such because it has no solutions for x, no real solutions for x. Now, if you want to know what that means in more detail, there's a video in this playlist about what no solutions for x actually means. But this is an example of it. It doesn't touch the x-axis. Okay, so that's the difference between that and that. Now, the one in the middle. Right, let's have a look at that. Okay, just get some more paper. So y equals x squared, what was it? Plus 3x. Okay, now it's neither of the previous two. Take a look at this though. There is a common factor, x. X plus 3. And if you can spot the common factor, you can factorize this. And once factorized, you can graph it. Okay, so let's just review this line. Difference of two squares. This is merely a translation of x squared 25 points up the y-axis. This one you deal with by finding a common factor, which is x, and it factorizes to x into x plus 3. Right. Now we get to the most common type of quadratic that you'll see, which is a quadratic trinomial. And there's a variety here. There's a bit of everything here. And like last time, we're going to start over here, because hopefully something like this is recognizable. This is a perfect square. That's my shorthand for perfect square. How do we know it's a perfect square? Well, if we halve this number and square it, we get 16. So half of 8 is 4, times 4 is 16. That's the test. And that factorizes really, really easily and quickly. So y equals x squared plus 8x plus 16. The factorized form of this is x plus 4, x plus 4. Two of these, which can be written like this. And that is a perfect square. Okay, so that's one of these out of the way. Now, turning to this one, this is an ordinary bog standard quadratic trinomial. And it is solved by finding the factors of 6 that add to 5. Factors of 6 that add to 5 are 3 and 2. So this factorizes to x plus 2, x plus 3. Okay, so that's a very, very simple one. And that would be the first... it would be my first instinct when confronting a quadratic trinomial to see if this works or it's something like this. Okay, so the majority of what you will deal with will probably involve this. It may sometimes be disguised, and here it is disguised. 2x squared plus 10x plus 12. Notice anything? Well, simply what's happened is this has been multiplied by 2. So we can take out this and we get x squared plus 5x plus 6, and you can factorize that in exactly the same way that you would factorize this. Okay, so that's this line. Now, it gets a little more complicated here. 3x squared plus 7x plus 2. 3x squared plus 7x plus 2. Let's get that written on my pad. Now, this is a quadratic trinomial. Our problem is that we have a number here that is other than 1. But good news, it's a prime number. So the way to approach this initially is to set up your brackets like this, because the factors of 3 are 3 and 1, so 3, 1. We also have a prime number here, which is really handy. The factors of 2 are 2 and 1. And using the power of prime numbers, we've factorized this thing. So what's the key to getting to this point? It's recognizing that you're dealing with prime numbers and seeing if this will work, because it will work in many, many cases. Okay, so that's that. This one, x squared plus 9x plus 5, well, it's not a perfect square. It doesn't have a common factor. There are no factors of 5 that will give us 9. It's certainly not one of these. It's certainly not one of these. What do we do? Well, having gone through the process that I've just gone through, so eliminating that, and that, what you can look at for this is either completing the square, which may be a little awkward because you're going to be halving this and squaring it, so it's going to be, you're going to be into fractions immediately, or using the quadratic formula. And if you're not compelled to make a choice, or rather if your choice is not made for you, I would use the quadratic formula to deal with this. And of course you can check using the discriminant to see whether there is in fact a solution for this. Again, there's a video on that elsewhere. Okay, so that's roughly quadratic trinomials, very roughly. I'm mindful that I do need to keep this video to a reasonable length. Now here we have turning point form, which again should be fairly easily recognizable. What this tells us is that this quadratic has a turning point at 2, 3. And this quadratic has a turning point at at 2, negative 3. Let me say that again, 2, negative 3. What's interesting and different about them is the following. So just let me get this written. X minus 2 all squared plus 3. X minus 2 all squared minus 3. I'm going to do this one first. So the turning point of this thing is positive 2, negative 3. It's down here somewhere. And it does that, roughly. Finding those points is a task for another day. But what it does have is it does have solutions for x. And this one, while it exists as a graph, does not have solutions for x, because although I've drawn this really, really badly, there we are, you can see it now, I've drawn this really, really badly, it's got a turning point at 2, positive 3. I know that's not to scale. But the important thing is that this does not touch the x-axis. So there are ways of looking at turning point form equations and going, there's no solution to that one. But this one does have solutions for x. And again, it's just about being able to recognize things. Okay, last one in this video. 2x squared plus 9x plus 10. Okay, so how do we approach this? 2x squared plus 9x plus 10. Okay, well, what is it not? There's no common factor. It is not a perfect square. Half of that squared does not equal 10. Is it possible that you can get factors of 10 to equal 9? Well, actually, yes, you can, because of the coefficient of x squared here. And so there are probably a couple of ways of going at this. But what I wanted to show you on this occasion is an example of factorizing by grouping. So what we're going to do is we're going to take this number and this number, which gives us 20, and we're going to look at the factors of 20, which are 10 and 2 and 5 and 4. 5 and 4 add to 9. I may have done this round the wrong way yet, but we'll see. Yes, I have. So I'm just going to rewrite this. 2x squared plus 4x plus 5x plus 10. Okay. Now, having split up the 9x into factors of 20, which I got from these two numbers, and ignoring my first attempt at grouping this, what I've got here is 2x squared plus 4x plus 5x plus 10, which I think you will agree 4 and 5 are 9. Now, watch this. We're going to do the following. We're going to take out a common factor, which is 2 and x. And we're going to put x there and 2 there. Okay? Right. Now, what's the common factor here? Well, it's 5. X plus 2. Now, notice the commonality here. Now, what that allows us to do is to group this and this, and factorize the equation this way. Now, this is not the only way of doing it, but this is factorization by grouping. And you sometimes see it presented in this form, but more often than not, you'll see it presented where you have 4 parts to the equation, rather like this. And that's really the subject for a further video. Now, what I want to do is just go back to our original piece of paper and just run through this quickly. Okay, so this, and this are all single-term quadratics. They're centered on the origin. The y-axis is their axis of symmetry. Then we have quadratics that come to us in 2 parts, difference of 2 squares, one where there's a common factor, one where x squared has simply been translated up 25 points on the y-axis. And I hope that you can see the differences there. Now, here, perfect square, pretty standard quadratic trinomial. Same thing with a common factor. And when you take the common factor out, you get this. to deal with. This is a quadratic trinomial, distinguished by having it's actually got 3 prime numbers in it, but that one and that one are the important ones. And they help you with its factorization. This one, it's the quadratic formula or completing the square, assuming that it does have a solution. Down here, 2 examples of turning point form. This one, because of the position of the turning point, has solutions for x. This one does not. And you've just watched me factorize this by grouping. As I said, it's not the only way of doing it. There are at least two or three other ways of doing it, but I just wanted this one example of factorization by grouping. Okay, now there are videos in this playlist on this channel dealing with each and every one of these. So if you've seen something here that you feel wasn't adequately explained, have a look on that playlist, and hopefully it'll all make a lot more sense to you. Thanks very much for watching. See you later.